To group one of the student exit presentations for the Autonomy Incubator here summer 2016. We have 8 presentations today covering a broad landscape of topics in autonomy, starting with Jeremy Lim, who has been with us 2 semesters now, 2 summers. He's from Penn State, and I will hand it over to Jeremy. Jeremy.
Hey, thanks everyone. Let's get started. All right, so hello, my name is Jeremy. I'm an undergraduate student at Penn State, and I will talk to you guys about Holy Grail, which is a big project that, well, several of the interns here at the Autonomy Incubator have worked on. So just a preview of what's to come in my presentation. I'd like to introduce Holy Grail, what this acronym and what this project is. I'd like to also talk about how that integrates with AON, which is part of the Autonomy Incubator's software development. Then I'd like to go over the Holy Grail architecture, how we've designed the architecture of this project. Then I'd like to go in closer and take a look at what I've worked on. Well, what I've worked on more with the command interpreter part of the Holy Grail. And then I'd like to go over future work with this project. And then I'd like to talk a little bit about how the incubator does its software development with agile development. And then I would also go through an example of what a chart that we would use in this kind of development environment. So without further ado, Holy Grail. It's quite an acronym. So I think I'll begin by going through it. It stands for Human-Operated, Language-Based Intuitive Interface with Gesture Recognition Applied in an Immersive, Lifelike Environment. It's quite a big acronym, but it's because we went with this acronym because the idea is big. When we were thinking about, when the Holy Grail team and us and Danette were thinking about this, when we pieced it out, we thought, oh, this is like the Holy Grail of all demos. So what is Holy Grail? Well, the idea of Holy Grail is actually kind of simple. We want to allow a non-drone pilot, somebody who's doesn't necessarily know how to pilot a drone or a quadrotor, able to control and manage a fleet of aircraft without, like I said, being at a high level without having to worry about the nitty and gritty details. We also wish to do this through a natural language interface. So instead of just sitting down at a desktop and clicking, dragging, etc., we want the user to be able to use gestures and speech to command these drones and their whatever mission that they might need to be doing. Additionally, we would like to have a feedback portion where we generate a virtual environment where we can see the trajectories and other parts of the mission that we've specified, so the user can have some feedback on what they've specified their drones to do. So, yeah, quick recap. We will use natural language to kind of specify a flight path or the mission for a couple of drones. The user will have feedback in virtual reality so that they know, hey, what is this path that I've plotted out? And then we actually fly the mission. And a good application and a good use case for this would be, say, maybe we want a scientist who doesn't necessarily know, hey, they don't want to pilot a drone or go through the effort of learning to fly. They just want to collect data over some certain area, and they want to be able to do this at a high level. So say maybe you had a scientist, they want to maybe they have a couple of drones with sensor payloads, and maybe, for example, they want to take pictures of terrain. So they want to be able to specify an area, go here, fly in a formation to kind of cover the terrain, and then gather the data. So here's the team of Holy Grail. That's me on the far right. That's Megan. She does our gesture recognition work. There's Angelica, who does our virtual reality portion of the job. And then we have Lauren and Javier, who work with our trajectory generation and risk map generation. Today you'll be hearing from, oh, and also not pictured is Erica. Sorry we left you out, but she does our speech recognition portion of the project as well. Tune in for Megan and Erica's presentations. They'll be coming later. Later today, you'll also be seeing Angelica, Lauren, and Javier's presentations to come. Yeah. So with Holy Grail, we wanted to kind of, this is the primary focus of this is to specify drone flight trajectories. Here's a drone, we want to specify where it flies to and how it flies. So we discovered, hey, there are a couple of flight modes that are of interest to people using this. We have formation segmented flight mode, where the user just specifies a regular geometric shape for the drone to fly. So maybe, hey, you want to fly this drone north, or just fly in a circle, or maybe a helix upwards. So that could be useful, like I said, for maybe covering an area for data gathering, or it is kind of a low-level flight path definition. There's also optimization mode. In this mode, we figured out that, hey, sometimes we just want to get the drone from this point to this point. We don't necessarily need it to fly in a specific formation. We just care about avoiding obstacles and maybe abiding by some certain parameters for this flight path. Maybe it's optimal in some way, maybe it's the shortest time, maybe it's the most fuel efficient. Lauren and Javier's work will go into this with much more detail. We also have the interpolation mode. This is similar to our geometric flight path mode, except in this mode, you would specify more than one geometric pattern. So the user would alternatively have the ability to say, hey, I want to specify a line and then a circle. Interpolation would be like, I would want to specify some shape, like maybe a square, for example, which is actually a composition of several lines, but we don't want to have the user be like line, line, line. So it is kind of an optimization of some sorts on the formation mode. And of course, after we define this path, the goal is to show it in virtual reality so that the user kind of gets a visual representation of what the flight path actually looks like when the drone would attempt to fly it. So backing up a little bit, Holy Grail is a couple of different software processes that people have written and that are kind of working together, sending data, talking to each other. So what we use for this project is the Incubator's framework for getting all of this different software to communicate with each other, and that is AON, Autonomous Entity Operations Network. It's, like I said, excuse me, the Incubator's framework for integrating different software processes together. And what we primarily use in this framework is DDS, which stands for Data Distribution Service. What is the Data Distribution Service, you may ask? Well, it is a communication standard put out by the Object Management Group. It is a standard for middleware that specifies how processes can communicate to each other on a network, on a publish-subscriber interface. So if you take a look at this chart real quick, you notice that for example, a software process might be, for example, somebody's running our gesture interface, for example, that exists in DDS as a participant. And this participant may have publishers and writers. And to transfer information from different processes, you write to a topic, which is kind of conceptualization of that data. So if you just want to send data from one place to another, you say, hey, writer, I'll write the information to the topic. And then you have your other process act as a reader and say, hey, reader, let's read from that topic. So DDS is a standard that allows us to do that really easily. The Incubator uses RTI's implementation of DDS. And there's a couple of advantages to this. It's network agnostic. We don't care if all the machines are on Wi-Fi or connected via Ethernet. We don't have to worry about the connectivity of the network while we're programming. We just have to have all the machines running all of our software on the same network. It's language agnostic as long as there's an interface for your language. So we don't care whether the nodes are written in C++ or Python. As long as that there exists an interface, yeah, we can work with that node. And you can have nodes that are written in Python, running, communicating with things written in C++, and et cetera. It's also distributed. If you're familiar with ROS, it's a very popular software package system that people use. That also runs on a publish-subscriber interface, but it's not very distributed. To run anything, you need to run a core program that does all the routing and stuff. With DDS, you can launch nodes individually and you don't have to worry about the core setup of the thing. You literally just launch all the different components of your project and they will talk to each other. So that's useful for connecting all the software together, having them communicate. So now I would like to kind of go into the architecture of Holy Grail. So we've kind of got a data flow left to right, sort of. We have our speech and gesture information. This is where the natural language interpretation comes from. And these are kind of semi-independent from each other. So what happens is that we get the speech information separate, and then we have the gesture information. And it's the job of the system to take that information, combine it, and make a complete trajectory message that we can send off to the trajectory generation component. That, of course, will be displayed in our simulation, which for this project, we've chosen to use Unity as our simulator, which is a game engine. And then after the user acknowledges, hey, this trajectory is good, we will send it off to our trajectory as waypoints to a vehicle interface, which goes to any sort of vehicle that would fly said mission. Note that there's kind of an implicit feedback loop here, because the simulation gives the user the information they need to know to decide whether, hey, this trajectory is good, this mission is good, or no, it's bad, I would like to start over, or etc. Kind of zooming in on one half of the architecture, so we're zooming in on the command interpreter portion. As I said before, it takes flight information from speech and formation types from gesture. So if we are in the example of we're sending a formation command, fly in a circle, well, the gesture portion would provide us, hey, what formation are we flying in? Gesture would provide, oh, it's a circle. But the gesture, that information by itself, not really enough to define a trajectory. You could say this is a circle and this is a bigger circle, etc. But it's really hard to tell without any additional information. That's where the speech information comes in. It'll provide, oh, radius or height or length, all those specific numbers that would be very helpful to if you're defining a trajectory. The command interpreter's primary job is to take both sources of information and combine them together into a trajectory definition that actually means something mathematically that you can generate a trajectory from. Note there's also a little bit of feedback from the trajectory generation back to the command interpreter. The command interpreter works as on the basis of, it takes in information and combines it together, but it's not supposed to do all the heavy math. So for example, if we want to specify a line and then another line on the end of that line, well, the trajectory generation will have to give back a little information to the interpreter so that it knows, hey, this previous trajectory ended somewhere, so that our next trajectory component is assumed to be pasted on top of the end of that or appended to the end of that list. So if we kind of move a little bit further in the system, we have the trajectory generation node again, but this time there's another information loop where we have our simulation interacting very closely with the trajectory generation. Now, when the trajectory generation creates a trajectory, well, we want to visualize it. So it's going to send the information to our simulation so that we get a great-looking flight path that shows the user, oh, what's the scale, is this correct, etc. Angelica will talk more about this simulation part of the project. So in addition to that, there's the potential for the user to modify the trajectory in the simulation. So for example, we can integrate a leap motion controller and allow the user to pinch and pull and kind of move these trajectories around a little bit, which would be like minor movements that are kind of hard to specify with gesture and speech alone. So these small movements, you can modify your curve in a small way. Yeah, maybe move this line over a little bit, maybe stretch out this helix a tad, and those modifications will go back to the trajectory generator, which will then, of course, send a new updated calculation back to the simulation. So in a sense, this would act as a back end, and this would act as the front end. But there is like I said, there is a feedback loop there that kind of modifies the trajectory. And of course, once it's given the OK, we'll send it to the vehicles. So now I've kind of gone through the Holy Grail architecture at a higher level. I kind of want to go back and talk about the command interpreter a little bit. So I want to run through two examples of the command interpreter taking messages and processing them. So the interpreter, once again, takes information from speech, which gives the formation specifications via information pair, so like height, radius, start position, end position, etc. Gesture would give information on type of formation, line, helix, circle, that kind of specification. The interpreter kind of works as a queue, a modified version of a queue. So in this example, the gesture topic has sent, we've read a couple information from our gesture. We've read line, helix, circle. We haven't received any information from speech yet at this point. But the interpreter's waiting, and so, but it looks like the gesture sent some more information on the gesture side of things. The goal of the interpreter is to send only messages that have both the gesture and speech information. So if we have a little bit of extra information from one side of the module for a short period of time, we'll queue up that information and kind of wait for our completing other half from, say, the other topic. So in this example, we've actually queued up more gestures, and we've kind of got 5 half messages lined up, but we're still missing information, and we can't send any information. Now a speech topic says, okay, we read a couple messages from speech. And in this case, if we happen to specify, we have the radius of this circle, we have clockwise, and that would get also queued up, but it would be queued up with the first, so in a sense it's parallel queue. So this would be queued up in a way so that it would line up with the first 3 on the gesture and so on and so forth. So if I added another message, that would add to that position there and that position there. The idea of this is that we're trying to preserve ordering of the messages. So if I say circle, helix, line, then the first 3, so if the first 3 messages of our gesture portion is circle, helix, line, then the first 3 messages of our speech topic are assumed to be matched with those 3 there. And so once we have a complete message, we will attempt to send it. So we're halfway here. We have the circle information, we have the radius information, but this message might not actually be complete. We could still be missing portions. So another part that the interpreter does is a recipe matching algorithm. So for this example, I'm going to take a line message. This message is complete. It has line, and it also has some information, speech information associated with it. But all it says is the end positions of the line. It doesn't say where's the start of the line. So the goal of this portion is to say, we know it's a line. We know there are a couple definitions of a line. For example, this definition would be start x, start y, start z, and positions. These are 3-dimensional points, 2 points. You can specify a line if you have a start point and an end point. Or another recipe where you have a start point, start direction x, you have a vector, a 3-dimensional vector representing a direction. Maybe this vector is normalized, and then a length. So you can also define a line that way. It depends on how the gesture specifies a line. You could say, I want this line to end at x, y, and z, or you can say, I want this line to go 10 meters north. Different kind of specifications for the line. So for this particular message, we have an end position, and we have to figure out, okay, we are probably targeting recipe number 1. So another source of data for the line is not only the message that's come from speech, but some implied and default fields that the command interpreter knows. So in this example, our start position, we have it set as 0, 0, 0, but these fields could be, for example, filled out from the trajectory generator. So if we sent a line trajectory generator previously, the generator says, okay, it ends at this point, this information is sent back to the interpreter, and the interpreter now knows, okay, we can assume that the user wants to add their new trajectory onto their old trajectory, and this is how that appears there. And some other default fields we can define. For example, we have length is 5. It's a default. It's meant for if the user specifies, oh, let's go north, but they don't specify a length. We would rather have the system try and generate a trajectory with some default length as opposed to saying, nope, can't do that. So we do a recipe matching. If we look at number 1, we know it matches because we can grab the information from the default data and our message, and then we can actually append that the missing information and send it off to trajectory definition. So this would be a complete message of a line. We know it's a line, start position and end position. If we look at recipe 2, we can fill a lot of the fields from the default data, but this isn't really where the user specified the line. They didn't specify direction length. They really specified end position. So yeah, these fields don't match with anything, and that's not the recipe we're using. We're missing some fields. So it's kind of a matching mechanism where we can know, hey, is this a line or is this a circle? And if we have enough information for them. Yeah, and that's kind of the basics of how the interpreter works. There are actually a lot more things we can add to this idea. The future works thing, there's a lot of things we could definitely do. For example, adding support for the interpolation connected trajectory mode. Megan's working on some interesting problems with that. So that is something that will be to come. We would also like to add, support for the user to pull information about the system. Can I ask how well the vehicle's doing on charge, if it's running out of battery, what's the altitude, etc. Also, expanding our support to multiple vehicles would be a very interesting topic that we could look into. And indeed, the command interpreter could definitely be expanded. I mean, we could obviously add a list to the list of possible formations and recipes that we want to do. Maybe we want to do like a Bosch-Fidon scanning formation or something. But also we could look in, also another future area of work is looking into building a command interpreter that's less rigid. The algorithms are described are kind of twists on really classic, the classic data structures of a queue, a list. And so we could look at more methods that taking more data into account. For example, I kind of made the assumption the first 3 messages of gesture match with the first 3 messages of speech, etc. But maybe that's not the best way to take a look at it. Maybe we want to take a look at and see, oh, what's the exact time this speech information came in? What's the exact time gesture information came in? And maybe that also changes the content of the message. Yeah, so that kind of is the end of the Holy Grail portion of this of this presentation. So I also wanted to go over kind of my approach and how the incubator does software development a little bit. So the approach that I took with building this project is, the incubator runs an agile approach, and I'll get to more of that in a second. I also attack this project using the Git revision system a lot to help organize my code, and I learned a lot more about it, just from using it. And another thing that I wanted to address is kind of the system construction approach. My job was not only to build the command interpreter and the system, but I also needed to build the interface, the DDS interface for each node. And that was interesting because we're using 4 separate languages for this project. We're using Java, We're using Java for the speech interpretation, MATLAB for the trajectory generation and risk assessment. We're using C# for our interfacing with Unity, and C++ for the command interpreter and gesture stuff. So I kind of had a crash course in seeing how this DDS interface works in all these different languages. Very interesting experience, to say the least. And yeah, going into agile development a little bit. So the idea is that there are several levels of kind of checking in and seeing how the progress is going on a particular project that we do as an incubator. We start with the daily scrum, which is, we list out, what's troubling us, what are the issues we're tackling today, what are we doing today, and that's kind of like a low-level, sort of informal kind of catch-up. Then we have our weekly sprint, which is more formal. We present a short PowerPoint presentation kind of on what we're what we are doing and what we are looking forward to doing and how we're doing in general. And that feeds into monthly showcases, which are basically the large showcases that we hold as an incubator, large demos, to kind of show off, hey, this is the work that we're doing, this is what progress we're making. And that, of course, feeds into our quarterly storyboard and demo. And of course, the hope is with that is that helps us feed into the whole mission of the incubator, making autonomy more accessible, and yeah. And I would like to show you kind of an example of one of the charts I used for one of the sprint tag ups. We call it a quad chart. We list kind of our objectives, our approach with those objectives, and kind of our milestones, what we've done so far. Looks like here I was working on the final review demo. This was right past the final review demo, and I was working on some system architecture design. So it's just a quick chart that we use to kind of catch up with each other in a slightly more formal way than just an informal scrum or something. And then of course we list our next steps. Here it looks like I was still working on the interpreter node. It's kind of in yellow. I made progress, and it looks like I had trouble with this portion here. So, but this is all listed out. It is all organized so that somebody looking at this can say, in general, hey, how's it going and what are we working on? And so that's kind of a sample of what we do during, say, a sprint. And that's kind of important to how we develop software in Incubator. Yeah, and that kind of concludes the bulk of my presentation. I'd just like to thank everyone for being very patient. The Holy Grail team in general, we've been working really hard on this, and definitely a special shout out. All the civil servants and contractors definitely helped so much. I asked so many questions. Ben, Jim, our software development team is excellent. Matt in particular, he's been working really hard on our Unity DDS bridge so that we could get the simulation version talking with the rest of DDS. That was a real challenge, and he really stepped up to it. Thank you to Net for being our cheerleader and kind of our visionary for this project. Everyone in the Autonomy Incubator as well, too. And the NIFS admin team. We wouldn't be here without them. Yeah, that's all I have, everyone. Any questions?
Time for one question for Jared.
So question asks the question whether if this is intended more for field use, you're there at the site, the drones are all ready to go, and you're gesturing them to go, or if you're back at the lab trying to simulate this mission beforehand, preparing beforehand. And to answer that, the way it's currently designed now, it's definitely more aimed towards beforehand, where you can kind of sit in a controlled environment, gesture, build your trajectory, and then see it as a feedback. But the gesture and speech components just by themselves, well, you don't need a keyboard or mouse for them. So for this system, yes, it's more suited to a stationary planning phase environment, maybe not as suited to being out in the field, but with more development on speech and gesture recognition, and maybe some interesting integration of vehicles, maybe we could have a point where, hey, we can actually walk up to a drone and say, hi, drone, go over there. You know what I mean? So I say that's kind of down the road a bit, I think. I think that once if Holy Grail grows, I feel like that's where we could be headed, is in the field kind of setup. Does that answer the question?
Yes, it does.
Okay.
Thank you, Jeremy.
Nope.